Okay, good evening, everyone. So, am I audible? Is my screen visible? Okay, so let's start this week's live session. So, we'll be discussing problems based on finding eigenvalues and eigenvectors of matrices and their diagonalization. Okay, okay. So this is our first question, and we have to find the eigenvalues of this matrix, given matrix. So, what is an eigenvalue? So for a given matrix A, we say that a vector V, which is a non-zero vector, and we say that lambda is an eigenvalue for matrix A if if we have some vector V which is non-zero, such that when you multiply the matrix with that vector, you get the lambda times V. So this vector gets scaled up by a factor of lambda. Okay, so such a lambda is called an eigenvalue. Okay, and this vector V, this is called an eigenvector. So this V is called an eigenvector for lambda. Okay, so for finding these values of lambda eigenvalues, we have observed that whenever this AV is equal to lambda V, we must have A minus lambda times identity matrix multiply with this vector V must be 0, right? And because we want to find such non-zero vectors for which the system of equation gets satisfied, that means we must have that determinant of A minus lambda I to be 0, right? Because if determinant is non-zero, then we will have a unique solution, and that solution is a zero vector. Okay, so this equation, that determinant of A minus lambda I, gives us the values, eigenvalues. Okay, and we will be going to do this for this particular matrix. Okay, we have to find the eigenvalues of this given matrix. So let's find the determinant of this A minus lambda I. Okay, so what are entries of A? Is 6 minus lambda minus 2 and 2. 3 minus lambda minus 1, 2 minus 1, and 3 minus lambda, right? We have to find its determinant. Okay, so let's find what is this determinant. 6 minus lambda times lambda minus 3 whole square plus 1. So this is minus 1 plus 2 times 2 lambda minus 4 plus 2 times 2 lambda minus 4. Okay, okay, just write this expression. What is this expression? Let's see, lambda minus 3 whole square minus 1. Okay, so this is equal to lambda square minus 6 lambda plus 8, and this can be written as lambda minus 4 to lambda minus 2, right? So here we have minus of lambda minus 6 into lambda minus 4 into lambda minus 2, and here we have 8 times lambda minus 2. So we can take lambda minus 2 common. It's negative. Let's take minus of lambda minus 2 common. In the bracket, we have lambda minus 4 into lambda minus 6 and minus 8. Okay. So this will give lambda minus 2 whole square into lambda minus 8, right? Why? You can ex write this, expand this part. So you'll have lambda square minus 10 lambda plus 16. Okay, and that can be written as lambda minus 2 into lambda minus 8. Okay. Okay, let's call this polynomial as a polynomial in lambda, p of lambda. Okay. Now lambda is an eigenvalue if and only if the determinant of lambda this a minus lambda is 0, and this determinant is 0 if and only if this p lambda is 0, if and only if lambda, the values of lambda are 2 comma 2 comma 8. So there are three eigenvalues. So right, so one of them is repeated two times, so this 2 is repeated two times. Okay, so if an eigenvalue repeated two times, then we call it as its algebraic multiplicity. Okay, so there is a term that is called algebraic multiplicity. So algebraic multiplicity of lambda equal to 2. Let's just write algebraic multiplicity of 2 is 2, because it's repeated two times, so its algebraic multiplicity is 2, and algebraic multiplicity of 8 is 1. Okay, so these are eigenvalues with their algebraic multiplicities. Okay, now we have to choose correct options out of these four. So we have seen that 2 and 8 are eigenvalues of A. So 0 is not an eigenvalue of A, so we can cross it. And the third option is algebraic multiplicity of the smallest eigenvalue is 1. So what is our smallest eigenvalue? So smallest eigenvalue is 2, but its algebraic multiplicity is also 2. So this is wrong. And the fourth option is algebraic multiplicity of largest eigenvalue is 1, and that is correct because the largest eigenvalue repeats one only once. Okay, so correct options are A and D. Okay, so are there any questions?
No, sir.
Okay, so let's start with the second problem. Okay, so here we have a matrix of order 3. So matrix of order 3 means it's a 3 by 3 matrix. So there are 9 entries. It's a 3 by 3 matrix. So there are 9 entries. Okay. Some order 3 by 3 matrix. We don't know what is it. And it's given that lambda 1, lambda 2, and lambda 3, these are eigenvalues of our matrix A. So this matrix A, 3 eigenvalues, which are lambda 1, lambda 2, and lambda 3. And we have to find the eigenvalues of this matrix, which is you subtract C times identity matrix from A and take its square. Okay, so let's see what will be eigenvalues of this matrix given eigenvalues of A. Okay, so for eigenvalues of A, we must have this relation to get satisfied, that A V must be equal to lambda times V for some vector which is non-zero. Okay, so now let's subtract C times identity. Okay, and plus C times identity. We can add and subtract this thing because they will just cancel each other. So we can write it here. This must be equal to lambda times V. So A minus Ci times V plus C times V is lambda times V. Okay, so we have just opened this bracket. Now this will imply that A minus Ci times V must be equal to lambda minus C times V. Okay. Now since this vector was non-zero, this is already a non-zero vector. This means that the lambda minus c must be an eigenvalue of the matrix A minus c times identity matrix. Okay, so we have this relation, but we have to find eigenvalues of the square, the A minus ci square. Okay, so now we have this relation. Let's see what we'll have when we have this square. Okay, so this square times v must be equal to A minus ci applied two times, right? You apply this matrix two times to v. Now this thing is equal to lambda minus c. So you can write A minus ci to v, lambda minus c times v. Now because lambda minus c is just a constant, you can take it outside and you will have again A minus ci times v. Again you can apply this equation. Let's call it 1 here. Then you will have lambda minus c whole square into v. Okay. So this shows that the eigenvalues of A minus ci whole square are lambda 1 minus c whole square, lambda 2 minus c whole square, and lambda 3 minus c whole square. Okay, because this equation, the second equation, this says that if lambda is an eigenvalue of A, then lambda minus c whole square must be an eigenvalue of A minus ci whole square. Okay. Okay, so here the correct answer is B. These are eigenvalues of A minus ci whole square. Okay, so any questions? Okay, so let's move to the next problem if there are no questions. Okay, so here again a matrix is given and you have to calculate this value, that take the fifth power of the matrix A and subtract the 4 times third power of the matrix A and something. Okay, so if you can do it directly if you want, but there are better ways to find it. We can use the Cayley-Hamilton theorem. Okay, so what is the Cayley-Hamilton theorem? It says that if you take the characteristic polynomial of the matrix A, so okay, so what is characteristic polynomial? It is just the determinant of, take A minus lambda times identity and you take the determinant. So this is our characteristic polynomial P of lambda. And this Cayley-Hamilton theorem says that instead of lambda, if you put A, P of A, then this must be 0. Okay, so every matrix satisfies its characteristic polynomial. Okay, so for this problem, we will use this theorem, Cayley-Hamilton theorem, and first we will find out its characteristic polynomial. Okay, so the characteristic polynomial for A, let's denote it by symbol PA, PA lambda here, must be the determinant of this matrix A minus the lambda times identity. So if you write that matrix, that will be 1 minus lambda minus 2 minus 2 and minus 1 minus lambda, right? Okay, so if you find this determinant, then you will have lambda square minus 1 minus 4, and that must be lambda square minus 5. Okay, so this is our characteristic polynomial, and the Cayley-Hamilton theorem says that if you put instead of lambda A, then this must become 0, the 0 matrix. That means the A square must be equal to 5 times the identity matrix. So this relation we have here. Okay, now we will use this relation that A square is equal to 5 times the identity. Okay, so we have to find A to the power 5 minus 4 times A cube minus 4 times A. Okay, but we know that a square is 5 times identity. So this a to the power 5 can be written as a times a square into a square, okay, 4 times a into a square and minus 4a. And now instead of a square, we will write 5 times identity. A, 5 times identity, 5 times identity, 4a, again 5 times identity, and minus 4a. Okay, so we have 25a minus 20a minus 4a, and that is equal to a. Okay, so this particular expression turns out to be equal to a, so that is our correct answer. Okay, so are there any questions?
No, sir. Continue.
Okay, thank you. So let's move to the next problem, the fourth problem. Again, the fourth problem has the same nature. We have here we have to find the inverse of this matrix A. Note that we can find the inverse of this matrix by usual methods. There are various methods to find its inverse, but here we will use the Cayley-Hamilton theorem. So this problem is actually an application of the Cayley-Hamilton theorem. So again, we will just find this characteristic polynomial, which is PA lambda, and instead of lambda, we put a. So that will just give us an equation in terms of the matrix, and then we will find its inverse. Okay, so let's find the characteristic polynomial, which is just the determinant of a minus lambda I. So what is our matrix? 2 minus 1 1. Okay, so 2 minus lambda minus 1 1 minus 1, 2 minus lambda minus 1 1 minus 1, and again 2 minus lambda. Okay, okay, so we'll get this here if you expand from the first row. And so what is this particular factor? Let's solve it here in the corner. Lambda minus 2 whole square minus 1. This is lambda square minus 4 lambda plus 4 minus 1, which is plus 3. And then we can again factor it. This is lambda minus 1 into lambda minus 3. So here we can write minus of lambda minus 2 into lambda minus 1, lambda minus 3, and 2 times with 2 times lambda minus 1. Now we can take lambda minus 1 common. In bracket we have lambda minus 2 into lambda minus 3 and minus 2. Okay. Okay, so if you expand it, you will just get lambda cube minus 6 lambda square plus 9 lambda minus 4. Okay, negative of this. So this is a characteristic polynomial, and now by Cayley-Hamilton theorem, instead of lambda, if you put a, then this must give you 0. That means that a cube minus 6a square plus 9a minus 4 times identity is 0. Okay, So now what we'll do, we'll just multiply both side by A inverse. So if you multiply both side by A inverse, this will become A square, this will become 6A, this will become 9 times identity matrix, and here we will have 4 times A inverse, right? Then we can write it here on the right hand side. This is 4 times A inverse. Okay, so this will imply A inverse is equal to 1 by 4 times A square minus 6A plus 9 times identity. Okay. So here option D is correct. So this is easier way to find out the inverse of the matrix, or another way to find out the inverse of the matrix. Okay, so any questions? Okay, so if there are no questions, let's move to the next problem. Okay, so here we have to find the dimension of the eigenspace corresponding to the smallest eigenvalue. Okay, okay, so what is eigenspace? So the eigenvalue, so first we will find all the eigenvalues and then we'll pick out the smallest eigenvalue. Now, for a particular eigenvalue, the collection of the subspace generated by all the eigenvectors is called eigenspace. Okay, so we have an eigenvalue and then we have this equation that AV is equal to lambda V, where V is non-zero. This V is an eigenvector. Okay, so the space generated by all the eigenvectors is called the eigenspace. We can write the space or the subspace of the vector space. We can say the subspace generated by all the eigenvectors of lambda is called eigenspace of lambda. Okay, so let's first find out the eigenvalue and then we will find all the eigenvectors. Okay, for eigenvalue, again we have to put this determinant A minus lambda times identity to be 0. So this will imply that determinant of A. 3 minus lambda 2 1 2 3 minus lambda 1 0 0 1 minus lambda. Okay, so you can see that these two entries are 0, so we can expand this determinant from the last row and we'll have minus of lambda minus 1 into lambda minus 3 whole square minus 4, right? Just expand this one. This will be lambda square minus 6 lambda and plus 9 minus 4 is 5. This can be written as, so we can factorize this quadratic equation and this will give us lambda minus so lambda minus 5 into lambda minus 1. Yeah, same thing. Okay, so what are all the eigenvalues? Of AR 1, 1, 5. Okay, so the eigenvalues are the roots of this polynomial. Okay, and there are 3 roots, one corresponding to this factor, one corresponding to this factor. So they get repeated 2 times, and then one corresponding to this factor. So there are these eigenvalue. And what is the smallest eigenvalue? Smallest eigenvalue is 1. So we have to find the eigenspace corresponding to this smallest eigenvalue. Okay, and then we have to find its dimension. So dimension means how many linearly independent vectors are there in that eigenspace which generate the eigenspace. Okay, so for finding those eigenvectors, what we have to do? Okay, you can see that we have this equation, right? That V is an eigenvector whenever AB is same as lambda V, where V is non-zero. Okay, So for finding such vectors, now the lambda is known. Now we know the lambda, so we just put the value of lambda as 1. Okay, so instead of lambda, we just write it AV equal to V. Okay, this will say that A minus the identity matrix times V must be 0. Okay, so we have to solve this system of equations. So this is a homogeneous system of equation, and we have to solve for it to get the values of the vector V. Okay, so what is A minus identity matrix? So for finding A minus identity matrix, just put lambda equal to 1 here because lambda is 1. So you have 2, 2, 1, 2, 2, 1, and then 0, 0, 0. Okay, this is our matrix A minus identity. Okay, now we have to find the solutions corresponding to this system of equation. For that, we will just reduce it to the row echelon form. Okay, so for reducing it to the row echelon form, subtract first row from the second row. So we will have 2, 2, 1, 0, 0, 0, and 0, 0, 0. Okay, so there are only one pivot. This is our pivot column, and the two columns don't have any pivot, so these are free variables. You can so there are these two are free variables. Okay, so free variable means you can assign any values to these vectors. Okay, so this means this implies that if your vector is, let's say your vector is v1. Okay, let's, instead of v1, let's write x1, x2, and x3. That means this says that the 2 times x1 plus 2 times x2 plus x3 must be 0. Okay, so what we will do, let's, because x2 and x3 are our free variables, let's take x3 equal to beta and x2 equal to alpha. Okay, this implies that x1 must be minus alpha by 2 plus beta. Okay, okay, so now first put alpha equal to 0. So any vector x1, x2, comma x3, how can we write it? X1 as minus alpha by 2 plus beta, x2 is alpha, and x3 is beta. Okay, so this can be written as, take alpha common, and you have here minus half 1, 0 plus beta times 1, 0, 1. Okay, so you can see that any vector in the eigenspace can be written as a linear combination of these two vectors. And these two vectors are clearly linearly independent because none of them is a multiple of another. This implies that the dimension of eigenspace is 2. The dimension of eigenspace corresponding to lambda equal to 1 is 2. Okay, so there are two linearly independent vectors in the eigenspace. So the correct option here is C. Okay, any questions? Okay, then so let's move to the next problem if there are no questions. Again, here we have to find what is the dimension of eigenspace of this matrix corresponding to the eigenvalue 0. So it's given that this matrix has eigenvalue 0, and we have to find the eigenspace or the dimension of the eigenspace corresponding to that eigenvalue. Because this eigenvalue is 0, that means we have to solve this system of equation that A minus 0 time identity V is equal to 0. That is AV is equal to 0. We have to solve the system of homogeneous linear equation, and for that the matrix is here. So this is our matrix, and you can see that this matrix A can be row reduced. If you write in echelon form, row echelon form, then you can see that there are already two rows which contains 0 and two rows which have entry 1. Okay, so we can subtract second row from the last row, so that this will become 0, and we can exchange first and second row. So if you are exchanging first and second row, then this 1 1 comes on the top, then you will have 0 0 0 0 0 0 0, and from the last row we are subtracting the first row. Okay, that means this will also become 0 0. Okay, again only the first column has a pivot, so that means there are three free variables, and because there are three free variables, that means dimension of the eigenspace must be 3. Okay, as we have seen in the last problem, the number of free variables determine the dimension of the eigenspace or the dimension of the null space, that we know previous even before, right? You can you can say that the dimension of eigenspace of eigenvalues lambda is same as the dimension of the null space of the matrix A minus lambda times identity. Okay, so here, because the dimension of the null space is same as the number of free variables, and there are three free variables, that means that is the dimension of the eigenspace. Okay, so this is our sixth problem. Let's move to the next problem. Okay, so here we have to find values of A for which this matrix is diagonalizable. Okay, so what do we mean by a matrix being diagonalizable? We say that a matrix is diagonalizable if A can be written as in this form, that P D P inverse. Okay, so if we able to write A as in this form, in this product of these three matrices, where P is an invertible matrix and this D matrix is precisely a diagonal matrix. Okay, so D is a diagonal matrix. So then we say that the matrix A can be diagonalizable. Okay, so in this case, okay, so how do we do this? We find eigenvalues of matrix A, and then the diagonal matrix is precisely the matrix containing all the eigenvalues on the diagonal. Okay, so the D matrix in general have this particular form, that here we put all the eigenvalues lambda 1 to lambda n, and everything is 0 above the diagonal and below the diagonal. Okay, and this P matrix is a special matrix. Its columns are, okay, so I'll just write the column. Its columns are eigenvector corresponding to lambda 1, eigenvector corresponding to lambda 2, and up to n. Okay. This is how it is done. You take P as this matrix containing all the eigenvectors corresponding to eigenvalues, and D as this diagonal matrix. So if this you have these eigenvectors to be linearly independent, that means if the matrix P is invertible, then you can write A as PD P inverse, and the matrix is diagonalizable. Okay, but this is a simpler problem. You can see that if you put A equal to 0, so if A is 0, then this matrix A is 1 0 0 1. So this is an identity matrix, so it's already a diagonal matrix. Okay, so that is your answer, that for the values of A, this you can diagonalize it. But this problem can be done directly also. Another way, let's find the eigenvalues of this matrix. So to find eigenvalues, that A minus lambda I, this matrix will be equal to 1 minus A minus lambda, and A minus A, 1 minus A, 1 plus A minus lambda. Okay, so this is our A minus identity, but we are finding its inverse, right? Determinant. Okay, so if you compute this determinant, then you will get 1 minus lambda square. So this determinant is 1 minus lambda square. So this will imply that eigenvalues are 1, 1. So there are two eigen values which are equal. One is repeated two times, and now we just find the eigenspace or eigenvector corresponding to this eigenvalues. Okay, for finding eigenspace, we have to solve this equation that a minus lambda is 1, so a minus identity times v is 0. Okay, so what is a minus identity matrix? This is minus a, minus a, and a. Okay, now you can see that this is row equivalent to, we subtract first row from the second row, then this is minus a comma a 0 comma 0. Okay, now notice that if a is non-zero, okay, so if a is non-zero, that means the first column has a pivot, okay, but second column will not have a pivot. That means there are only one free variable. Then the dimension of eigenspace corresponding to 1, the lambda equal to 1 is 1. Okay, because there is, if a is non-zero, then there is only one free variable, and that is the dimension of the eigenspace. Okay, but then you will only have one linearly independent eigenvector. Okay, but we need two linearly independent eigenvector. Okay, so this will imply that the matrix will not be diagonalizable, that a is not diagonalizable. So if a becomes non-zero, then matrix cannot be diagonalizable. Okay, so for a to be diagonalizable, if and only if a must be 0, right? Because if a becomes 0, then there are two free variables, there are no pivots, and if there are two free variables, that means the dimension of eigenspace is 2. That means there are two linearly independent eigenvectors, and using those two eigenvectors, you can form a matrix P, and then you can write a as PD P inverse. Okay, so but you can see that when a is 0, then this matrix itself become an identity matrix, and it is in the diagonal form. Okay. Okay, let's move to the next problem. Again, you have been given two matrices A and B, and again you have to find a matrix P so that A and B are similar. Okay, so similar means you can write A as P B P inverse. Okay, so if there is a matrix P, so that you can write A equal to P times B times P inverse, then you say that matrix are similar. That A and B, these matrices are similar. Okay, and so we have to find this matrix P. So for which matrix P, A and B are similar. Okay, so notice that B is a diagonal matrix. Okay, since B is a diagonal matrix, so eigenvalues of A are, so there are two eigenvalues, 2 comma 3. Okay, or 3 comma 2, right? Or you can see it like this also, that what are eigenvalues? These are determinant of A minus identity, but A is equal to P times B P inverse minus lambda times identity is determinant, which is same as determinant of P into B minus lambda identity into determinant of P inverse. Okay, this is simply determinant of B minus lambda I. Okay, so the determinant of B minus lambda I, the roots of that equation are just 2 and 3. So A and B have same eigenvalues. Okay, So we already know the eigenvalues of matrix A. They are 3, 2. Now we have to find the matrix P. Okay. For finding matrix P, we have to find those eigenvectors with respect to 3 and 2. Okay, let's find out the eigenvectors for this particular matrix. Okay, first, start with lambda equal to 3. Okay, we have to solve this equation that A minus 3 times identity into V is 0. For that, what is A minus 3 times identity? This matrix is minus 4, 6, minus 2, 3. Okay, now this is similar to, if you can just divide the first row by 2, and this is minus 2, 3, minus 2, 3. Subtract first row from the second row, you will have minus 2, 3 and 0, 0. Okay, that means the first column is a pivot and there is one free variable, and because there is one free variable, the dimension of this eigenspace is 1. And let's write V as x1, x2. Okay, so from this equation, you will have minus 2 times x1 plus 3 times x2 must be 0. Okay, let's take x2 equal to 1, or let's take x2 equal to 2. For x2 equal to 2, but we have x1 equal to 3, right? If x2 is 2, then x1 must be 3. So one of the eigenvectors is 3, 2. Okay, now let's do this for 2 also. Lambda equal to 2. For that, A minus 2 times identity is equal to minus 3, 6, minus 2, 4. Okay, so divide the first row by 3. So if you divide first row by 3 or minus 3, let's divide by 3, then you have minus 1, 2. And divide the second row by 2, then you have minus 1, 2. Now subtract these first and second row, and we have 0, 0. Again, there is only one pivot column. So that means there is one free variable. So we have one linearly independent eigenvector. Okay, so that means minus x1 plus twice of x2 must be 0. Okay, put x2 equal to 1, and we have x1 equal to 2. Okay, so the second vector is 1, 2. Okay, so the matrix P must be the first vector 3, 2, and the second vector 1, 2. This is our matrix, and for this matrix, A is equal to P times B into P inverse. Okay, this can be checked. Okay, so this is our correct answer. The D is correct. 3, 2 and 2, 1. Okay, any questions? Okay, so if there are no questions, let's move to the next problem. So the next two problem, they are based on some application of diagonalization. Okay, so if our matrix is diagonalizable, then what the benefit of that? So this is the first problem based on that. For this given matrix A, we have to find the A to the power 100. Okay, so what should be the A to the power 100? Okay, so note that if you find directly A to the power 100, then this will be a lot of work, right? Multiplying A 100 times, that will be a lot of work. But if you able to write A in this term, that P D P inverse, where D is a diagonal matrix, then A to the power 100 is nothing but P D to the power 100 into P inverse. Okay, now because D is a diagonal matrix, so in this case D will be just some lambda 1 0 0 lambda 2 Okay, so d to the power 100 is will be easy to calculate. It is just lambda 1 to the power 100, 0, 0, and lambda 2 to the power 100. Okay, so for solving this problem, first you have to write a as this product, that PDP inverse. Okay, and for that we have to find this matrix D and this matrix P. Okay, so the matrix D is the diagonal matrix containing eigenvalues, and P contains eigenvectors. So we have to find eigenvalues and eigenvectors. Okay, so first let's find eigenvalues, and for that we have to find the determinant of this matrix. Okay, so this is 1 minus lambda, 2, 4, and 3 minus lambda. Okay, so what is the determinant of this? This determinant is x lambda minus 1 into lambda minus 3 minus 8, which is equal to, you can write it lambda square minus 4 lambda minus 5, and then you can again factor it, lambda minus 5 into lambda plus 1. Okay, so eigenvalues of the matrix A are, there are two eigenvalues, one is 5 and one is minus 1. Okay, so because now we have our eigenvalues, the matrix D must be on the diagonal. We can have 5, minus 1, 0, and 0. Okay, so D is this matrix. Let's find the matrix P. For finding matrix P, we have to find the eigenvectors corresponding to these eigenvalues. Let's state first lambda equal to 5. So for lambda equal to 5, we are solving this equation that A minus 5 times identity of V is 0. So we are solving for non-zero vectors where V is non-zero. Okay, so what is A minus 5 times identity? Okay, so 1 minus 5, which is minus 4. So this is minus 4, 2, 4, and minus 2. Now this matrix is similar to this. Divide the first row by 2, you have minus 2, 1. Divide the second row by minus 2. We'll have again minus 2 comma 1, and then this is similar to subtract these two rows, you get 0, 0. Okay, so there is one pivot column and one free variable. So let's write our eigenvector as x1 comma x2. That means twice of x1 plus x2 must be 0. Okay, so you can see that x2 equal to 2 and x1 equal to 1 is if solution. Okay, so one solution is enough here because this is one dimensional. So our first vector must be 1 comma 2. Okay, let's find the second vector for lambda equal to minus 1. For lambda equal to minus 1, we are solving this equation that A plus identity times this vector is 0, where V is non-zero. Okay, so what is A plus identity? This is 2 comma 2, 4 comma 4. Divide last column by 2, you have 2, 2, and now subtract these columns, or you can divide also. So when you subtract, you will have 0 comma 0, and then divide by 2, you have 1 comma 1. Okay, so this is the, so again one pivot column and one free variable. Okay, so this will just give us that x1 plus x2 must be 0. Okay, so you can see that a vector, we can choose x2 equal to 1. So if If you choose x2 equal to 1, then x1 must be minus 1. So this is another eigenvector. Okay. And now we have our matrix. So the matrix P must be, it contains the eigenvectors. Okay. So because the first entry in the diagonal is 5, so you have to put the first eigenvector as the eigenvector of 5, which is 1, 2. 1, 2, and minus 1. So this is our P. Okay, that means now we have can write A as PD P inverse. So A to the power 100 must be P D to the power 100 P inverse. That means, so what is P? It's 1, 2, minus 1, 1. What is D to the power 100? Okay, so D was 5 minus 1, 0, 0. Okay, if you take 100 power, then you will have 5 to the power 100, 0, 0, and 1. Okay, because minus 1 to the power 100 is 1. Now what is inverse of P? Okay, so if for finding inverse of P, what you do? You have 1, 1, and this will be 1, 1 minus 2. And then divide by the determinant. So what is the determinant? Is 3. So this is 1 by 3. Okay. So what is this product? Okay, so if you multiply all these equations, then multiply all these matrix, then you will get 1 by 3 into 2 plus 5 to the power 100 minus 1 plus 5 to the power 100 minus 2 plus 5 to the power 100 2 times, and 1 plus 2 times 5 to the power 100. So this is our answer. This is 8 to the power 100. Okay. The C is correct option here.